Good morning, I'm Jean-Louis Van Belle. I'll be talking about quantum physics again today. Um, the title of the presentation is Everything You Need to Know About Quantum Physics because, yes, we're gonna very briefly and very quickly cover everything you need to know about it or everything you want to know about it. There's six topics. I'm going to be talking about forces and the fundamental forces, electromagnetic, nuclear, and then we're going to be talking about the particle models, one of the big things that you won't read in classical textbooks is what's the model really of an electron, what is it, and a proton and a neutron as a composite particle. So we've developed some mass without mass models about these things, and we're going to be talking also about the measurements, so how you explain mass, the magnetic moment, radii, etc. We don't want to be talking particle reactions, basically decay, unstable particles, and going to make final remarks on gravity, which is kind of a weird force, if it is a force. So here we go. On the top you have what we call orbital energy equations. So the energy in an orbital is the sum of kinetic and potential energy, and yeah, you have them there. So for the Coulomb force, kinetic energy is the same for Coulomb force and electromagnetic force and nuclear force. It's mv squared over 2. That's relativistically correct because we're talking, a tangential velocity. And the difference between the nuclear force and the Coulomb force, the electromagnetic force, is in the structure of the force. We have a range parameter for the nuclear force. It's much stronger at shorter range, and at the longer range, the Coulomb force is predominant. And so we model that with these equations in which you see these mu parameters, standard parameter of the Coulomb force, standard parameter of the nuclear force. And I put a minus and a plus sign because in a moment I will sort of be modeling a neutron as a proton and an electron together. And so this is going to be some combination of a nuclear force and an electromagnetic force. And also the minus sign is there, of course, because, like charges, the same charges will repel each other electrically, but they will attract each other in the nucleus. That's why protons stick together. We think protons stick together because they're in close range and the nuclear force kicks in, and that's why they stay together. So that explains the minus and the plus sign. In terms of magnitudes, if you calculate like magnitude, so you would need to compare these ratios. They come out to 1 actually, so they're a bit of the same nature. What differs really in the form factor or in the structure of those forces is that range parameter that comes in. I put some calculations then in regard to the electromagnetic force. We will do that in a moment. Sort of model the radius of an electron in an atomic orbital, and that's the Bohr radius RB that you have there. And we know we have a principal quantum number 1, 2, 3, 4, which determines which electron orbital we are talking about, the first, second, third, and yeah, that sort of relates. With, of course, the principal quantum number is there, n squared, with the Bohr radius. So if we're talking the first electron orbital, n is 1. So then the radius of the electron orbital is just the Bohr radius. But we can relate it to the Compton radius. The C there are C, and C is there for Compton, not for Coulomb. Well, it's of course it's electromagnetic force. So yeah, so the C do have are linked up. But we can see that sort of the Bohr radius is the inverse of the fine structure constant alpha times the Compton radius. And so we can also write that as a function of the classical electron radius, or we can write out the fine structure constant as we're doing there. And from these formulas, we know that classical electron radius will again be an alpha ratio of the Compton radius, and that's what we write out there. And so you have an idea of scales. The Compton radius is 0.386 times 10 to the minus 12 meter, so we're talking the picometer scale there, while the classical electron radius is the femtometer scale, 2.82 times 10 to the power minus 15. So these are the basic equations, and you can do a lot of stuff with them. Basically explain atoms and also nucleus. So magnetic moment of an electron, you know, there's sort of that thing with the anomaly of a magnetic moment. Magnetic moment is generated by a current. A current is put it there as a charge times the frequency it passes in a loop. So QE times the frequency, and then we calculate that from the Planck-Einstein relation. E is h times the frequency. So we get a huge current actually. 19.8 amperes in an electron, in a free electron. And the magnetic moment then is the current times the surface of the loop, so it's PA squared. We can write that all out, and now we get a nice relationship between the radius and the magnetic moment. The larger the radius, for the same frequency, of course, the larger magnetic moment we will get. But you know how this plays out is that the frequency is determined by the mass and the radius and all that. So you get one equation for the magnetic moment. Which we have there, 9.28, and an enormous number of figures, and you should actually put a minus sign in line with conventions, but that's sort of the Kodata value for the magnetic moment almost. But we know there's a small anomaly, and how can we explain that? If you sort of think of a charge in orbital motion going around and around, and you think of that charge maybe having some dimension itself, which we think it has, you know, the classical electron radius is much smaller than that quantum radius of a free electron, which is the radius, the effective interaction radius with photons when you fire them at electrons. But yeah, we think there's something like a classical electron there and a classical small charge, point-like charge. And you can calculate that out because if we distinguish between sort of an effective versus geometric center of charge, you can see that there. We have a geometric center of that charge, but if it's in some orbital, you know, there will be more charge outside of the orbital than inside, and so we have an effective radius that is different from the mathematical geometric radius. So we can calculate that out. The frequency is going to be, you know, again, the ratio of the velocity divided by the radius. So we have v for the effective velocity and r for the effective radius. And we actually find out, but it's purely mathematically, that the effective velocity will be slightly larger than the speed of light. And so that's just a geometric mathematical thing, because we know nothing travels faster than light. The whole charge as a whole, that point-like particle, point-like charge in its orbital will travel at speed of light, because its rest mass is 0, and you know, it has an effective mass because it requires velocity, relativistic mass. So, but yeah, that works out all right. We get that alpha divided by 2p factor, the Schwinger's factor, which you know, is explained very mysteriously by, you know, field theory and other complications, but complicated theories. But you should just look at things in a very simple way. Charge sort of seems to manifest itself in different sizes. You know, an electron orbital is much larger than a free electron, and then within the free electron we have the classical electron, small point-like charge. And so yeah, that's sort of the question that is there. Is there some kind of should we think in terms of a fractal structure of charge? So these are interesting questions to think about. At the moment, we sort of can't really decompose that classical electron into something more than the classical electron at very small point, like 2.82 femtometers, a large thing, or small thing. So let's move on to the proton. Said a proton, we think of that as a nuclear oscillation. A nuclear oscillation, we have that range parameter, but what's also different is that the force structure is different. We think of like two oscillations that are perpendicular to each other, so we can add the energies. And so these two oscillations will each pack half of the total energy of the proton. And we also think they're going to pack, well, if they pack half of the energy of the proton, then, you know, it just comes out of the equations. They should also pack half a unit of Planck's quantum of action. And so then we can use that mass without mass model again. You know, interpret C as a tangential velocity. We use for the frequency the Planck-Einstein relation, and we write it all out. Then we get the radius of a proton, and you see we have a factor of 4 there in the what we could call the Compton radius, but you know, we know it's a nuclear oscillation, so we should perhaps find another word. So it's h bar divided by the mass of the proton times c, and we have a fourth factor there. I'll come back to that fourth factor. So we can then again calculate, there you have it, the magnetic moment of the proton, and we should compare it, of course, to the measurements. The measurements of JLab pre-RAD in 2019 sort of solved what was referred to as the proton radius puzzle and came out with that measurement, 0.831 femtometers. So we have a difference there, and maybe that's an anomaly. We should investigate that. And I said the funny thing is sort of the radius of a proton is about 4 times smaller than the classical electron radius. So we have that 1/4 factor there, which also indicates, we can look at those forces and this and that, but basically it's the structure of the force that differs between the nuclear force and the electromagnetic force. So going back to the calculations on the magnetic moment, you can write that all out. You get sort of, well, first we calculate the magnetic moment, actually, the formula for the relation between the magnetic moment and the area. So if we there plug in the codata value, the measured value of the magnetic moment, we actually get a radius that is 0.5871. So that differs by a square factor of 2 squared, with the actual radius, and we relate that again to the fact that the nuclear oscillation packs 2 oscillations, so we should think of it as a spherical particle rather than something oscillating in a plane like with an electron. So there's different form factor there, and if we multiply that again with 2 squared, we get we get the exact almost exactly the JLab pre-RAD radius. So we think that's pretty good. Based on the magnetic moment, we calculate a radius. We have the assumption of a form factor, and it all comes out. So now we're going to the neutron. I said we're thinking of the neutron there on the left as a positive and a negative charge that are being attracted to each other when they're at close range, but nuclear force, and but they repel each other electromagnetically. The figure is a bit misleading because we still think that, I said the proton is like a heavier, or the positive charge there is the positive charge is sort of oscillating itself in some kind of nuclear oscillation, while the electron is an electron and oscillates an electromagnetic oscillation. So magnetic moment, we'll start with that actually. We have these formulas below, which I'll explain in a moment. But we have the magnetic moment of a neutron, and it's sort of minus 0.9, etc., with a lot of figures there, but it's of a much smaller order of magnitude. And so we gave the proton magnetic moment, so we can sort of think like, okay, the magnetic moment of the neutron is just the addition of the magnetic moment of that proton oscillation and then the electron oscillation. And so yeah, if we know the proton magnetic moment, then we should be able to calculate the contribution of the electron oscillation. And so we get that difference, and we get something that is kind of reasonable. The difference indeed between the neutron magnetic moment and the proton magnetic moment corresponds to a radius of about 1 femtometer, which is a bit larger than the measured neutron radius, but again you have that factor 2, which is linked to the spherical nature of the oscillation of the force, and then it comes out at 0.7, which is good enough. So yeah, the energy of the neutron divided by the mass by the neutron is a strange relationship. The mass energy equivalence relation is always equals to c squared, and we can apply the energy competition theorem, which says half of the energy should be in the nuclear oscillation and the other half in the Coulomb oscillation, and then we sort of we replace that by these orbital energy equations, and then you work that all out, and you get a very nice formula, which gives R as a function of that nuclear range parameter A, and for the rest we just have well, the formula is actually for 1 minus beta squared. Beta is the relative velocity, is V over C. So yeah, that's a formula. Think about it, and it's a nice formula. Can we sort of determine the range parameter? Yes, based on that formula, we should be, we have sort of an empirical value for the neutron radius and the proton radius, and so putting all these formulas together, we should get something sensible for the nuclear range parameter, and it's in the range of femtometers. So now I'm going to be talking about particle reactions decay. First, need to say sort of, you have heard about wave functions. Wave functions are complex exponentials. We write them as a. It's a real coefficient. Yeah, literature you will see it's complex exponential and this and that and calculations. But in the end, it always turns out to be, if you combine everything, to be real. If you solve the Hamiltonians and then we multiply that by E Euler's number to the power. An imaginary exponent, E times the phase delta. So the nature of matter antimatter is according to me, is in the plus minus sign of the coefficient a. We can have plus or minus a times e to the power imaginary unit times the phase. And so the direction of spin, every matter particle or antimatter particle can have two directions of spin. That's in the plus or minus sign of the imaginary unit. So I write that out. So I have a wave function for S, sort of a stable particle, and S over bar as bar with is the antiparticle, and so that's what you get when you write it all out. Suppose these are stable, so we write actually the argument of the wave function delta as alpha t. And alpha will be equal to the energy divided by h bar according to the Planck-Einstein relationship. So it's stable. There's no decay there. If we have decay, that's what we have below, a wave function of an unstable particle and its antimatter counterpart. Then we should add a beta parameter, I beta, and that's going to model, that's going to add a decay coefficient, and I write it all out. So you have your normal wave function a times e times imaginary unit times alpha t times a real exponential, because e squared is minus 1. And so we have a real negative exponent, Euler's number to the power minus beta t, and beta is going to be the inverse of the mean lifetime of that particle, but it's gonna die out. So that's how you model stable and unstable particles and matter and antimatter. Another way of thinking about it, it's very interesting, is that what I write there for matter, we have actually, Euler's formula, e to the power to an imaginary power is a cosinus times that phase plus the imaginary unit times the sinus. And we know the sinus is actually the same function as a cosine, is just lagging behind by 90 degrees in radians p divided by 2. So two functions, but one, the imaginary part, is lagging the real part by 90 degrees. And we think sort of the electromagnetic force, has an electric field factor, and a magnetic field factor. And the magnetic field factor actually lags the electric field factor by 90 degrees. So that sort of introduces a bit of an asymmetry, I would say, in the force, and explains all these CPT symmetries, combined CPT symmetry. But yeah, the Occam's razor, that's how Dirac discovered a bit the positron. As there's this other possibility, antimatter, mathematically, and if we write that out, then we find that the imaginary part of that wave function will precede the real part by 90 degrees. So we write it out, minus cosinus the phase. We think of the phase here as an angle. Who measures the real some real number. So that's equal to cosinus phase of the phase plus minus sinus delta is plus cosinus delta plus p divided by 2. So we have an imaginary part here which precedes by 90 degrees. So that's kind of interesting. I sort of discussed on ResearchGate a little bit, people don't like that, antiforce, what is that? But it's very interesting, because it would explain, that other antimatter coming with an antiforce and a different symmetry, right-handed versus left-handed in the force structure. It would explain the dark energy and the dark matter in the universe, because that would be antimatter, and everything they radiate out would be also antiphotons and antineutrinos, and they don't interact with ordinary matter. So all of the dark energy and the dark matter in the universe would be just antimatter. Problem solved. Okay, we're gonna go to the next. So that's the decay. I put one here for K mesons, kaons. You see, I talked about it in the previous presentation. We can sort of see how things happen in cloud chambers, or the electronic equivalent that they use nowadays. And so you have different particle reactions and different possibilities, and some things happen and some things don't happen. But yeah, I'll refer to my previous presentation. We model that basically by, there's a state in, two particles going in, and that's on the right hand side of that, the B of in figure 11.5, which I take from Feynman's lectures. We have an anti-kaon, a neutral anti-kaon going in, and meeting a proton in that liquid hydrogen, basically proton nucleus. What comes out is then a lambda, a neutral lambda, and a positive pion, and that sort of decays then further into, again, a proton, negative pion, and the pions, they decay then further in muon electrons and ordinary electrons. They combine to stable particles again, that whole accident. And so we're just going to focus on that interaction between the first interaction. I guess the sequence of events we have, but the first event is really that neutral anti-kaon and the proton combining to yield a neutral lambda particle and a pion. So we model that by a system of equations, and when you write that all out, using these alpha and beta parameters to model unstable particles, and using the minus sign to model the antimatter nature of that anti-kaon, well, that's what you get. And so that's what they call then the scattering matrix, or the S matrix, which you need to find. And then you can simplify these things by assuming certain form factors. That's what the quark hypothesis is all about, but I don't buy into that actually. So gravity then, the final one. Gravity is a weird one, because if we sort of model the orbital energy, if we equation for the orbital energy equation, the kinetic and the potential energy add up to 0. So you might say there's like no energy in the in a gravitational orbit. And that's really funny, but that makes actually a lot of sense, because if you don't think of it as a force, then you really think of matter curving space in such a way that small objects in the vicinity of a massive object will follow what they call a geodesic. The geodesic depends, the curvature of space depends on the masses that are involved, of course, so it's not something static. It's not space-time that is that's curved from itself. It's not some kind of aether there. No, we have two objects, and they sort of define space around them. And I calculate sort of, if we would treat it as a force, which is easier for calculations, of course, then we see a completely different order of magnitude. There's a bit of a mistake on the slide there. The ratios should work out to 4 times 10 to the power. No, it's okay actually. 4 times 10 to the power 42. So Coulomb nuclear energy, we might do the same for the nuclear force, is about 40 times 40. Well, not 40 times 10 to the power 42 times stronger than the gravity. So that's another reason why gravity really stands out as a sort of a different beast, and Einstein's general relativity theory sort of made sense of that. So that's it. I'm at 20 minutes. I think that's enough. I hope you enjoyed this, and don't hesitate to sort of look at the papers. They work it out, and they're much more lengthy, but they explain things pretty well. Thank you for listening.